In this video, we talk about accelerating a charge between two charged plates. You see the figure here. We have two charged plates. There is an electric field set up then between them, and the plates are separated by a distance z. And we have an electron here whose charge is given as little e and whose mass is given as capital M. And it says here that we wish to derive an expression for the speed, v final, of the electron when it hits the positive plate. It's going to start down here at rest, and we want to know with what speed it hits. Let's put electric field lines into this figure. They should be uniformly spaced, and they should point away from the positive charge and toward the negative charges. Write an expression, number 2, for the electric force on the electron while it's in the presence of the electric field. The electric force is given by Q times the strength of the electric field that Q finds itself in. And that's pretty much the right answer. However, the charge here is given not as Q, but as lowercase e. So I think what we want here is the force that this electron will feel should be written like that. We want to express our answer in terms of the variables that were given in this particular problem. Number 3, our part B answer is not only the electric force, it's also the net force on the electron. Gravity is completely negligible. Use Newton's second law to write an expression for the acceleration of the electron. Newton's second law says that the net force on an object is equal to its mass times its acceleration. The net force is little e times big E, and M here is given. You can barely see it there at the top of the screen. It's a capital M. So we need to change that, multiplied by A. So the acceleration of this electron is going to be A is equal to little e times big E divided by big M. Now, let's use a kinematics expression that contains our unknown variable. That would be Vf. And our knowns to obtain an expression for V final of the electron when it hits the positive plates. What other knowns do we have? We know that V naught is equal to 0. The electron starts from rest. We know the displacement of the electron because that is the separation between plates. Let's refer back real quickly. You can see that that separation is given as the variable z. So our displacement is z. And we know the acceleration. We just derived this expression, little e times big E divided by big M. What we don't know is time. And so therefore, I think we should use the kinematics equation that I refer to as the no time equation, which is Vf squared is equal to V naught squared plus 2 times the acceleration times the displacement. V naught is 0. The acceleration is little e times big E divided by M, and delta x in our problem is z. So I think Vf can be written as 2 times little e times big E times z divided by big M square rooted. Number 5 says, let's verify part 4 by using conservation of energy. The energy of the electron is its charge multiplied by the potential that it has. Here, we don't have Q, we have little e. That is the way the charge is given. And this voltage difference is the electric field multiplied by the separation between plates. Well, here, we're doing a lot of crossing off, aren't we? The separation between plates is given the variable z. So what that means is that the initial potential energy is essentially little e times big E times z. If all of that potential energy is turned into kinetic, the final potential energy will be 0. We know that the initial kinetic energy is 0. So what that means is we need to equate these two quantities here. So let's do that. Little e times big E times z is equal to 1/2 times the mass of the electron, which is capital M, multiplied by Vf squared. And what does that give us for VF. The 2 goes there, the m goes there, take the square root. I'm getting 2 little e, big E, z divided by m square rooted. Look at that. That is pretty neat. I'm going to give myself a smiley face right there. Boop. We're getting that result to match. Let's finish up here with number 6. The electron's acceleration was constant because the force and mass were both constant. Which method that we used above, Newton's laws plus kinematics or conservation of energy, would work, even for cases in which acceleration isn't constant? And the answer to that would be conservation of energy. Kinematics equations, like the one we used, the no-time equation, those hold only for cases when the acceleration is a constant. If the acceleration is not constant, you cannot use those simple kinematics equations. But conservation of energy holds in a broader number of cases.